Okay, so let's discuss a couple of examples related to Fourier transform. So this particular exercise basically covers the discrete Fourier transform. Discrete Fourier transform. Okay, so we know that for the discrete Fourier transform, so this is the discrete Fourier transform expression. So we have n equals minus infinity to plus infinity xn e to the power minus j omega n. So the xn is actually, this is discrete signal or discrete sequence. So this may be either finite or infinite. So the finite means length is a kind of a finite value L. So infinite means length of the sequence is actually infinity. So if you, for example, if you take this un, so this is basically infinite length sequence. Infinite length sequence. So the, if you remember, un is basically defined as 1 for n greater than or equal 0 and 0 otherwise. So if you plot it, so it's something like that. So you have so this is un. So these kind of sequences are basically identified as infinite length sequence. So the rest of the sequence which we discussed previously, so they basically have a finite length or finite number of samples. So n is actually ranging from some minus n to plus n kind of. So then if you basically evaluate the number of samples, so the number of samples is a finite value. So those sequences can be identified as finite length sequence. So if you have sequences having this infinite number of samples, so those are basically infinite length sequences. So xn is a discrete sequence, and once you evaluate this x omega, so this is your discrete Fourier transform of xn, where xn is a discrete sequence. Okay, so this is the fundamental formula which we basically use in those examples. So I'm referring the exercise 1 in the shared presentation, x1. So here, so it says that we have a finite length sequence xn equals 1 for this range. So from 0 to 4, we have non-zero values for the xn. So if you go through this one, so it's something like that. If you draw it, so this is n 0, 1, 2, 3, 4, Fine. So if you draw it, it's something like that. So this is the exam actually. So this is exam. So the length of the sequence L equals 5. So we have 5 samples, but n is basically in between 0 and 4. So if you take the values of n, so we have n equals 0, 1, 2, 3, 4, and rest of the values of n is basically 0. So this is your example. So then you are asked to evaluate the Fourier transform of xn and asked to plot the magnitude and phase spectrum of the signal. So how do you get this Fourier transform? So you can just apply this equation x omega equals. So now we can simply say that, so this is a finite length sequence, so we can simply truncate the summation from n equals 0 to 4 xn e to the power minus j omega n with this. So this particular sum has infinite samples, but so the example we basically discuss here has finite samples. So we have 5 samples, so the summation would be simply truncated into n equals 0 to n equals 4 xn e to the power. So here, so we can simply substitute, like this is a kind of a, so if you further simplify, it's something like that. N equals 0, 4, xn is basically 1. So this is e to the power minus j omega into n. So this is a kind of a geometric series, and you can take the sum of these finite terms. So this is equals to 1 minus r to the power n. R is actually to the power minus j omega. N is the number of samples, so we have 5 divided by 1 minus r. So this is the sum of 5 terms of a geometric series. So you may heard about this Gunottara Sreni. So this is the sum of this 5 terms of this Gunottara Sreni, or the geometric series. So now it's up to you to simplify this expression further. So we can do this. So if you get this kind of fraction of this exponential terms, so we can simplify it using this model. So this is the simplification. So you can take the half of this exponent. So you can simply take e to the power minus j omega 5 by 2. And in the denominator also, we can simply take that. So if you take this out, so you have 1 here, so you can add e to the power j omega 5 by 2 minus, so if you multiply this, so you have 1 here minus e to the power j omega 5. Similarly, you can take the half of this exponent, So then it becomes e to the power minus j omega half. Here you can add e to the power j omega half minus j omega half. So then, so you know that if you have this difference between this complex conjugate term of this exponential term, so this is a kind of a complex exponential function, and this is its complex conjugate. If you have this difference between these two quantities, so you know that we can easily replace this with sinusoids. So you know that if you have sine theta, so this is like e to the power j theta minus e to the power minus j theta divided by 2. So you can simply substitute this here. So then it becomes, so this can be simply replaced with sine phi omega over 2. Here we can replace this difference sine omega over 2, and you can basically simplify this exponent x2 exponential function. So then you can bring this to the numerator, so it becomes 4 omega. So something like that. So then ultimately xj omega, so x omega equals, so you have a sine phi omega over 2 divided by sine omega over 2 into e to the power minus j 4 omega. So this is the final formula. So this is the Fourier transform of this discrete sequence xn. Okay, so then so next is actually how do you get this magnitude and phase. So this is x omega, so you have sine phi omega over 2 divided by sine omega over 2 into e to the power minus j 4 omega. So you can easily get the magnitude. So how to get the magnitude? So the magnitude of this exponential is basically 1. So the magnitude becomes magnitude of this sine phi omega over 2 divided by the magnitude. So sine. So this is, or else you can take the magnitude of this entire function. So then the angle of this x omega, so let's assume theta omega. So this is the phase spectrum. So this is the magnitude spectrum. So the phase spectrum is actually, so you can take, so this is the phase. So this is the phase spectrum. And again, keep in mind, so we have two quantities. So this is the general phase, assuming that this component, assuming that this block is always positive. So this block so depending on the sign, because in some cases, like if you just plot it along with the omega value, so sometimes this because we know that it's the sine function is something like that. So this is your sine. So if those values, once you take a particular omega value, and if you multiply it with this 5 or 2 or half, so then the whatever the value basically produce as a sine of this entire angle, if those angles are lie here, so you can claim that the sine of that one is positive. If the values are basically now in this negative region, so the sine functions basically introduce a negative or minus 1. So this may be either plus 1 or minus 1 depending on the value of these two blocks. Because we basically plot the spectrum, along with omega. Okay. So if you basically evaluate this phi omega over 2 and omega over 2, so the value of this sine value of this particular components give either a plus value or minus value, because the magnitude is captured here. So the magnitude is captured here. So sometimes depending on the signs of these two quantities, so you may have additional sign minus value appear in front of you. So then basically you can treat those components as well here. For example, so depending on this, so there may be two possibilities. One is like if, so I'll take this quantity as A. If A is greater than 0, so then the exponential or the phase is basically minus 4 omega. So if A is less than 0, so you have minus sign in front of this. So this minus sign can be basically absorbed to this exponential. So we know that e to the power j phi means cos phi plus j sin phi. So the sin phi is actually 0, cos phi is actually minus 1. So then we can basically absorb this minus sign as a e to the power j phi factor. So then the phase is like 4 omega plus phi. So this is like absorb the negative sign as a e to the power j phi. So if this particular quantity, so if this block A, if this is a plus value or positive value, the phase is basically Now the spectrum is basically equals to minus 4 omega. If this A factor is less than 0, it means in addition to the magnitude, we have a minus sign in front of this. So that minus sign can be absorbed to the phase as a e to the power j phi term, and then the phase spectrum would be minus 4 omega plus 5. So keep in mind that. Okay, so then you can basically plot it using a kind of a tool like the MATLAB or something else. So you can simply get the magnitude and phase spectrum, but until this mathematical derivation, you can basically get the answer. Okay, so this is the solution for that one. So then we can move to the exercise 2, EX2. So in that exercise 2, we have an infinite sequence, infinite length sequence xn equals half to the power n un. So this is half to the power n un. So this is a flavor of unit step. So then, so you are asked to evaluate the Fourier transform of this particular extent. So you can just apply the equation x omega equals minus infinity to plus infinity xn e to the power minus j omega. So from this, you know that this is basically defined, un is basically defined for n greater than equals 0. So the summation can be simplified to n equals 0 to infinity. Xn is now half of n e to the power minus j omega n. If you further simplify it, absorbing this half also into the term n equals 0 to infinity. So you have e to the power minus j omega divided by 2 to the power n. So this is again a geometric series, and you are asked to evaluate the sum of infinite terms. So n goes from 0 to infinity. So this is a sum of infinite terms of this. So just apply this series sum of this geometric series. So it becomes 1 over 1 minus r. 1 minus, so the factor is here, half e to the power minus j omega. So this is the x omega. So this is the solution. So here you can simply say that sum of so this is the theory. So this is the answer. Okay. So then you are asked to evaluate the Fourier transform of this function. Now we have, so you are asked to evaluate x omega, let's tilde. Now this x is this. So this is the simple time reversal. So this is time reversal of xn. So you can just refer the Fourier transform of this time reversal function. Okay, so this is not a time reversal, sorry. This is not the exact time reversal of this one. So we'll see like this. So xn is actually half n. So what about x minus n? So this is the time reversal. So then this is becomes minus n u minus n. If you simplify it a bit, so this is like okay. We need to evaluate the Fourier transform of this block. Half to the power n u minus n. So this is the definition, this is the previous section, half to the power n u n. So if you take the mirror of the time reversal, so this is the time reversal of xn. So if we just substitute n with minus n, so you have x minus n half to the power minus n u minus n. So this is the time reversal of the xn. So this is the time reversal of this xn. But we need to evaluate this function half n e to the power. So what we can do is we can simply obtain this x tilde n using time reversal. So this x tilde n is actually 2 to the power 2n 2 to the power minus n u minus n. So if you just simplify half to the power 2n and half to the power minus n, so you'll ended up half to the power n. So this is basically half to the power n. And here u minus n. So this is actually x tilde n. But by looking at this block, so this is actually x minus n. Okay, so if you know the x omega, so this is the Fourier transform of xn. So the Fourier transform of x minus n is actually x minus omega. So then you can simply write expression for the x tilde omega, the Fourier transform of x tilde n equals half to the power 2n. So we have x minus n there. So the x minus n, the Fourier transform of x minus n is actually x minus omega. So this is equals to half to the power 2n x omega is actually 1 over 1 minus half to the power minus j omega. So you can simply take that 1 minus half e to the power j omega. So this is the solution for this. So the x omega equals 1 over 1 minus half e to the power minus j omega, and x minus n, the Fourier transform of x minus n is like minus omega. So using this property, you can just get the value of this, or the Fourier transform of this, the function. So the third question, so third exercise. So here you are asked to evaluate the Fourier transform of this function. Xn equals n minus 3. So by looking at this, so you should be able to identify that. So this is actually come from a shift. So this is the time shifted version of un by 3 units to right hand side. Okay, so this is basically comes from un, and it's simply shifted by 3 units to the right hand side. So then we'll take the shifted version of this original function. So if you have xn here, xn, so we'll take, what about xn minus 3? So instead of n, you can just substitute n minus 3. So this is the exact time shifted version of xn. So this is the exact time shifted version of this xn. So we are asked to evaluate the Fourier transform of this. So this is the exact time shifted version. So here you have 1 over 3 to the power n. So the exact time shifted version has a 1 over 3 n to the power minus 3. So then what we can simply do is we can adjust the terms. So we have to, so what we can do is, so we can simply put like this, minus 3, 1 over 3 to the power n, un minus 3. Okay, so this is x n minus 3. So by looking at this, you can simply claim that this is actually xn. So this is the xn. You need to evaluate the Fourier transform. Okay. So this is, sorry, we'll put like this tilde. So the xn, original xn would be this. if you take the shifted version of this is the original xn. So the shifted version is xn minus 3 equals 1 over 3 into the power n minus 3 un minus 3. And this so then if you reformat or readjust the numerical values, you can simply write it that. So this is your shifted version, xn minus 3 equals 1 over 3 to the power minus 3 into 1 over 3 to the power n un minus 1. So then basically you can identify that this is actually your x tilde n. So this is x tilde n. So then from this you can basically claim that the x tilde n equals 1 over 3 to the power 3 x n minus 3. Okay. So then x n minus 3 is actually a shifted version of xn. So you can simply claim that x omega, the Fourier transform of this xn is 1 over 1 minus 1 over 3 e to the power minus j omega. So this is, you can simply borrow it from the previous example. So previously we have 1 over 2 to the power n un. Now this time it's like 1 over 3 to the power n un. So you can just borrow the solution from the previous example. So the Fourier transform of xn is actually 1 over 1 minus 1/3 e to the power minus j omega. Okay, so then from this you can take the time shifted version. So that here the shift is 3, so you can have a factor of e to the power minus j3 omega into x omega is the Fourier transform of x n minus 3. So this is the Fourier transform of, sorry, this is the Fourier transform of. So you can simply replace this. So this is equals to 1 over 3 to the power 3. So you have e to the power minus j3 omega divided by 1 minus 1 over 3 to the power minus 7. So this is the finite solution of this. So this is the finite solution. Or else you can use these very fundamental equations to evaluate this. So let's see how we can do it. So you have xn, which is equals to 1 over 3 to the power n un minus 3. So if you take the definition x omega, so if you clearly observe that one, so this is basically defined for n greater than or equals 3. So then you can simplify the summation to this one. N equals 3 to infinity xn 1 over 3 to the power n e to the power minus j omega. Okay, so unfortunately we have this inbuilt equation, so the standard equations for the geometric series, where you can find the finite length or infinite length sum starting from n equals 0. So not from 3. So one would be like you can just evaluate the sum from this first two terms, three terms, 0, 1, 2, because here like, so this is a sum from 3, 4, 5 up to infinity. So if you take the original series, you have 0, 1 and 2 as well. So one would be like, so you can take the sum of this infinite terms and subtract the sum of 0, 1, 2. So this is one way. Or else we can adjust this like this. So we need to change the index starting from 0. So we'll take the substitution m equals n minus 3. So then if n equals 0, so you have an index of 0. So n equals 3. So this is starting basically a sum from 3 to infinity. So then the corresponding value for m when n equals 3 is 0. So m equals 0 if n goes to infinity. So infinity minus 3 again, m goes to infinity. 1 over 3. So you have n, you can simply replace this n with m plus 1. So n equals m plus 3. So n plus 3 e to the power minus j omega, n equals m plus 3. So then we'll simplify it. So here we have e to the power minus j omega 3, which is independent of this index m. So you can take this out. So then we have m equals 0 to infinity 1 over 3. And again here we have 1 over 3 to the power 3 here, which is again independent of m. So this sum is from 0 to infinity this. So this is 1 over 1 minus 1 over 3 to the power minus 0. So if you plug in that factor, so this is equals to, we have 1 over 3 to the power 3 and numerator you have it for minus j 3 omega, and denominator you have this. So you can take the same answer like in the previous. So this is basically using the standard definition for the Fourier transform. So the previously we used this time, the property of this time reversal, and just apply it. So the both ways are possible, but keep in mind depending on the question, so you may need to switch it to different methods. So the first method. So it's straightforward. By using this Fourier transform properties, you can get the exact solution. The second one is like you can start from the scratch, use the fundamental Fourier transform equation and get the solution done. So this is one. Okay, then the fourth example. So the fourth one, ex4. So here it's given that your xn equals delta n. So this is the discrete impulse. So this is discrete unit impulse. Okay. So this is basically defined at n equals 0. So the value is 1. This is delta n. Okay. So let's try to find the Fourier transform of xn. Find Fourier transform of xn, which is equals to delta. So just plug the equation x omega n equals minus infinity to plus infinity xn e to the power minus j omega. So the sequence has a single sample which is again at n equals 0. So this is basically simplifies to delta n e to the power j omega n. This is again for the simplifies to this is actually 1 at n equals 0. This is delta n is equals to 1 at n equals 0. Otherwise, the function is not defined. So then we can simplify it further. So this becomes 1 and this n becomes 0. So this is 1 e to the power minus j omega. Here this is only defined at n equals 0. So then this exponential term goes to e to the power minus j omega 0 and delta n goes to 1. So this is equals to 1. So if you plot it, so this is your discrete signal. So this is the corresponding Fourier transform. So this is the time domain representation. This is time domain. And this is frequency domain. So here you have a single path, single samples. If you convert it into a kind of a frequency domain, so it's like a flat line. So this is basically using this for noise samples. So in most of the textbooks, this is referred as additive white Gaussian noise. So if you have a time domain AWGN sample, so it's a kind of a flat response in frequency domain. Yes, then we'll move to the next exercise. Exercise 5. So you are asked to evaluate this xn equals cos phi n over 3. Okay. So if you have this kind of a trigonometric function, so easiest is like just convert it to the exponential, because so if you have this exponential, so you can easily manipulate or manage with this Fourier transforms, because the Fourier transform itself has a e to the power j term, and if you convert this expression to e to the power term, so then basically you can just sum these two e to the power terms together and get the solution done easily. So you can simply use this trick. So this is cos e to the power j phi n over 3 plus okay. So then, so from the property table, you can simply get that e to the power j omega naught n. If you take the Fourier transform, so this is equals to 2f phi L equals minus infinity plus infinity delta function series, infinite series of delta functions. So then just plug this to here. So then the x omega is actually half. So this e to the power this factor, Fourier transform of this block can be this 2 pi L equals minus infinity plus infinity delta omega. Omega naught is like 5 by 3 to 5. Then the Fourier transform of this one is basically 2 pi. So we can use another index delta omega plus 3 minus 2 pi. So you can just take this out. And the final solution will be x omega equals 5 from L delta. So this is the final solution. So the other example, so the last example, so you are asked to evaluate the inverse Fourier transform of this given function. So here x omega is given, so it is equals to cos squared omega. So you need to find xn, which is the inverse Fourier transform of x omega. So by the definition, so this is the definition of this Fourier transform. So if you just expand it for n equals 0, so you have x0, so e to the power minus j omega 0 is 1. So then n equals 1, we have x1, n equals 2, you have, likewise you have infinite term. So if n equals minus 1, so likewise. So here you have minus infinity, so this goes to plus infinity. So this is the expansion of this infinite sum. So by looking at this, so this is basically a series of these exponential terms. So if you can convert this x omega into a series of exponential terms and map it to here, so you can find the relationship between whatever the derived one and this one. So let's try. So you have x omega cos squared omega. So you can convert this because you know that cos they cos 2 theta. So this cos 2 theta equals this 2 times cos squared theta minus 1. So that cos squared theta is actually 1 plus cos 2 theta divided by 2. So you just apply it to here. So it's like half 1 plus cos 2 omega. So if you have cosine terms, you can easily convert it to exponentials 1 plus e to the power j omega 2 divided by 2 plus e to the power minus j 2 omega divided by 2. So this can be replaced with e to the power j 2 omega plus e to the power minus j 2 omega divided by 2. So then you can rearrange the terms and see. So here minus factors are in your right hand side and plus factors are in your left hand side. So you can put it like this. So ultimately you convert your Fourier transform expression into three terms, three exponential terms. So then you can just compare this with the expanded version of this. See, like this is x0, so this becomes x0. So then here 2 omega, so you can just plug it here. So then this is 1 over 4 is the term at, so this is n equals 0, so this is n equals 2, and the factor or the pre-factor is 1 over 4. So this is again this x minus 2, n equals minus 2, the factor is again 4. So if you simply see the x in, so this is something like that. So this is the zero. Or else you can use this delta functions and simplify that half delta n, which is at n equals 0, 1 over 4 delta n minus 2 plus 1 over 4 delta n plus 2. So this is the solution. Yes. So this is the couple of examples which I need and want to discuss here. So you can go through this slide sets and the this video, so you can have a kind of a better idea about how we can manipulate the expressions to obtain Fourier transforms and inverse Fourier transform using either Dirac approach. Just write the fundamental equation and get the solutions, or else you can use this properties. Sometimes rather moving with this straightforward direct approaches, so there may be kind of alternative ways of getting Fourier transform and inverse Fourier transform by mapping these equations, like which we discuss in this fifth and sixth examples. So I believe like this may clarify most of the issues you have. Thank you.